Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything we can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Can we get a fuel call? 5.4, 5.8, 15, 70, 6.4.
Pollution was always something we saw close up, or not at all, until the National Aeronautics and Space Administration gave us a global view from high above.
As the world's population continues to grow, our need to use our natural resources wisely becomes more apparent and urgent.
We're in an energy crisis now, and will be for some time to come.
Attention all passengers, Flight 307 is canceled until further notice.
We must change if we're going to have the energy we need.
Until very recently, the priorities of aviation science have remained unchanged. Only in the 1970s have the need for greater efficiency of men and machines led to new and revised priorities for aviation researchers.
A new airfoil shape called the supercritical wing is being flight tested aboard an extensively modified F-8 jet aircraft. Almost the direct opposite of conventional airfoil shapes, the supercritical wing has a flattened top surface.
The new shape weakens the shock wave that normally builds on top of conventional wings during flight,
allowing the aircraft to fly faster, more smoothly, and at lower operating costs.
And that concept ended up making a significant contribution. The supercritical wings are today used on almost every transport manufactured.
Had the supercritical wing F-11, which did supercritical wing demonstration.
The wings may be adjusted to various angles to achieve optimum performance at different speeds.
Studies indicate that if the design features of the oblique wing were applied to full-size jets, it would give them increased fuel economy.
The piloted version is now being built.
The AD-1. During takeoff and landing, the wing can be positioned at right angles to the body for maximum lift. But as the aircraft picks up speed, the wing can be pivoted to cut down drag, and therefore fuel usage. Another project geared to improve aerodynamic efficiency, winglets. Engineers modified this KC-135 transport by mounting vertical extensions on its wingtips.
These winglets act to increase lift and lower drag.
Winglets cut wind resistance. NASA scientists developed the advanced winglet technology to cut wind drag, thereby increasing airspeed and cutting fuel consumption.
Dryden researchers are using an F-111 to study ways of developing more efficient wing shapes. In the natural laminar flow experiment, they modified the plane's outer wing panels. This new wing shape eliminated turbulent airflow over much of the wing surface. For functional versatility, one of the most promising ideas tested here is the tilt rotor.
The XV-15 research aircraft combines the vertical takeoff capability of the helicopter with the speed, range, and fuel economy of a turboprop airplane. These types of aircraft use less room for takeoff and landing and keep noise and air pollution lower than our present commercial planes.
With the continuing fuel problems, engineers are attempting to make the big trucks more efficient.
It's believed that both trucks and recreational vehicles can be made more economical to operate.
Means of achieving aerodynamic efficiency on aircraft isn't that different than it is on automobiles and trucks.
Starting with a small delivery van, Ed Saltzman and his team of engineers reshaped the vehicle with sheet metal.
The aerodynamic improvements that we've experienced so far are translatable into 15%, perhaps 20% savings in fuel.
The researchers are hopeful as they continue to apply aerodynamic techniques to help solve a ground transportation problem.
During the 1970s in the aviation field, fuel rose from the least expensive operating cost for commercial airlines to the most expensive. By 1979, the cost of fuel quadrupled.
A digital fly-by-wire flight control system crucial to automation of the X-Wing's flight mode conversion and circulation control aerodynamics has reached the laboratory test phase. Has the dream of combining the best attributes of both helicopter and airplane been realized? The X-Wing system will begin flight tests later this year to investigate advanced rotor concepts. Its broad range of mission capabilities capitalize on its ability to combine the unique hovering qualities of a helicopter with the high cruise speed and range of an airplane.
The F-14 Variable Suite Transition Flight Experiment was originated to obtain accurate in-flight measurements of the boundary layer transition location for wing airfoil pressure gradients. The wing panels of the F-14 were modified to maintain laminar flow to a significant extent.
Because of the energy crisis, I was working on the Jetstar. We took the wing tanks off the Jetstar and we put an experiment for laminar flow control. This was like subsonic laminar flow control.
Birds change the shape of their wings according to various flight conditions.
The ideal wing would have a smooth contour upper surface and be able to rapidly and precisely change its shape to provide minimum drag for the amount of lift being commanded by the pilot.
The Wright brothers in their Wright Flyer also used wing warping. So the idea is not new, it's just that the technology has now developed to the point where it is practical.
This is the Mission Adaptive Wing. This flexibility is possible because we now have composite materials that will withstand nearly continuous bending without fatiguing, and lightweight digital computers that can operate at speeds sufficient to control the wing. Through in-flight contour changes, internal mechanisms bend flexible leading and trailing edge surfaces to the appropriate curvatures required to maintain the optimal aerodynamic effectiveness at all times. The Mission Adaptive Wing, an attractive technology for future military aircraft.
It's really the first time that a wing would actually provide optimum performance throughout a very large part of the flight envelope.
The C-140 Jetstar currently is test flying an advanced propeller model, which should lead to considerable fuel savings in future aircraft.
Basically, a forward-swept wing design is potentially more efficient in the transonic speed regime. The forward-swept wing has a supercritical cross-section about 1/3 the thickness of a typical supercritical wing. A discrete variable camber device is installed on the trailing edge of the wing. Set back on the fuselage, the forward-swept wing configuration also affords a more flexible payload distribution, which makes for a smaller, lighter aircraft. Tactically tougher to see, economically less costly to build, operate, and support.
The F-16XL aircraft is uniquely characterized by its large crank arrow wing. The aircraft will be used by NASA as test beds to evaluate aerodynamics concepts designed to improve wing airflow during sustained supersonic flight.
We know that we can get laminar flow an inch or so back. Now we're trying to maintain it further aft, and in order to maintain laminar flow further aft, we have to come up with some method of augmentation, and that's why we're using suction to actually pull the boundary layer back down and relaminarize the boundary layer.
We've actually perforated the surface of the wing with millions of microscopic holes, and we suck a portion of the airflow away from the wing to help keep it stable.
If you maintain laminar flow for a larger distance, you can reduce the drag of an airfoil, and if you can reduce the drag, you can increase your fuel efficiency. If you can increase your fuel efficiency, you can increase your payload capability. And, you know, it's just a whole raft of things that come out of being able to maintain laminar flow.
Ailerons are normally used to roll the aircraft, which is then used to turn the aircraft. We intend to use only the outboard ailerons and move them together, both up or both down, to change the tailoring of the wing so as to optimize the flow characteristics.
I can deflect the inboard section downwards while deflecting the outboard section upwards. This will create an unbalanced force on the wing, thereby twisting the structure in a new way, different than we've seen before.
These morphing structures of the future are likely going to be able to sense the environment and adapt, change their shape to particular flight conditions.
The design will be able to take material out, make the wing thinner, and that makes it a more efficient wing.
This is a project that's trying to see if there's an advantage to flying 2 or more aircraft in formation, much like flocks of birds.
Every wing creates a wingtip vortex, and if you can put your airplane on the part that's going up, then it's just like riding a wave at the beach.
The lead aircraft signals its position to the follower with a wireless modem. You couldn't do this without fly-by-wire. The vortex can be so strong that the conventional flight control system, it'll flip you out.
But it's a high energy source, and if we can properly map it and know where it is, and then use that energy to our advantage,
we're expecting to extract out a 10% drag reduction, at least a 10% drag reduction.
It's one of the first times that this has ever been tried with a civilian airplane.
What we wanted to expand was to use production autopilots, the FAA mandated data link.
Let's go ahead and try to step in toward the wing.
Ways that you could improve the efficiency of vehicles by not changing the vehicles at all, but by changing how we use them for operational efficiencies. Even if you didn't want to fly in the wake, if you wanted to, for instance, avoid the wake, you could still fly closer than what is currently allowed.
BWB is a combination between a regular aircraft and a flying wing.
It actually has a lower drag than a conventional aircraft.
It's like a hybrid car compared to a regular car. You're getting 20 to 30% better fuel efficiency.
By understanding the boundary layer transition, we can increase our understanding and our predictive capability for all types of aircraft, both for civil and for military aircraft.
People take it for granted nowadays that an airplane needs a rudder in order to turn. Think of every bird you've ever seen, none of them have rudders.
The Prandtl D aircraft is designed with a certain twist in its wing.
A different lift distribution.
A new span load on the wings. What we're really looking for is the positive correlation between roll and yaw.
Prandtl does not need wing widths. It does not need a vertical tail.
There's only 2 control surfaces. The design of Prandtl minimizes drag.
This doesn't have any hinges, it just bends. It morphs itself, if you will, sort of like a bird flies.
The efficiency of this technology is very significant, and it results in a fuel savings up to hundreds of millions of dollars of fuel savings a year.
A traditional wing has 1 flap and 1 aileron per wing. We broke those up into segments, and that allows us to reshape the load using localized input or small inputs rather than the whole control surface.
We'd like to develop some research that can be used to minimize the amount that structures deflect, minimize the amount that structures vibrate.
It's an attempt to redistribute the load into a more favorable configuration. That configuration will allow for lighter weight structures in the future.
The first step towards wing shape control is knowing what the position of that wing is, so that can be fed into a control system to then control the shape. Conventional sensor technology allows you to make a measurement every several feet. The FOSS technology allows you to have a sensor every 1/4 inch along the single optical fiber. That allows you to look more and more like a biological system. If you can save a few pounds of instrumentation mass or lead wire mass, that's more fuel and less cost. That fiber can remain on the vehicle throughout its life.
Now aircrafts are taken out of service and maintenance inspections are being applied to that at given intervals. Wouldn't it be better to take an aircraft out of service when your management computer has told you that it's time for service and here's why? The FOSS is capable of measuring critical parameters such as temperature, strain, liquid level, loads, and deflection.
I believe can really revolutionize the way we do our business in aerospace. And it has that spillover effect that can go into other types of industries like oil and gas, shipbuilding and health monitoring, high-rise health monitoring, all types of other applications.